All right, portability. Let's go. Almost there. Linux is a portable operating system that supports a wide range of computer architectures. Portability refers to how easily, if at all, code can move from one system architecture to another. We know that Linux is portable because it has already been ported to various systems, but this portability did not occur overnight. It requires diligence and a constant eye towards writing portable code. Consequently, it is now easy, relatively speaking, to bring Linux up on a new system. This chapter discusses how to write portable code, the issues you need to keep in mind when writing both core kernel code and device drivers. Portable operating systems. Some operating systems are designed with portability as a primary feature. As little code as possible is machine specific. Assembly is kept to a minimum, and interfaces and features are sufficiently general and abstract so that they work on a wide range of architectures. The obvious benefit is the relative ease with which a new architecture can be supported. In some cases, highly portable and simple operating systems can be moved to a new architecture with just a few hundred lines of unique code. The downside is that the architecture-specific features are not supported and code cannot be hand-tuned for a specific machine. With this design choice, optimal code is traded for portable code. Some examples of highly portable operating systems are Minix, NetBSD, and many academic systems. On the opposite side are operating systems that trade all portability for highly customized optimal code. As much as possible, code is written in assembly or otherwise designed for a specific architecture. Kernel features are designed around specific architectural features. Consequently, moving the operating system to a new architecture is tantamount to rewriting the kernel from scratch, and even if possible, the operating system might be ill-suited for use on other architectures. With this design decision, portable code is traded for optimal code. Such systems are often harder to maintain than more portable systems. Of course, these systems need not be more efficient than a more portable system. Their willingness to disregard portability, however, allows for a no-compromise design. Microsoft, DOS, and Windows 95 are two examples of this design decision. Linux takes the middle road towards portability. As much as practical, interfaces and core code are architecture independent C code, where performance is critical. However, kernel features are tuned for each architecture. For example, much fastpath and low-level code is architecture dependent and often written in assembly. This approach enables Linux to remain portable without foregoing optimizations. Where portability would hinder performance, performance generally wins. Otherwise, code is kept portable. Generally, exported kernel interfaces are architecture independent. If any parts of the function need to be unique for each supported architecture, either for performance reasons or as a necessity, that code is implemented in separate functions and called as needed. Each supported architecture then implements its architecture-specific functions and links them into the kernel image. A good example is the scheduler. The large majority of the scheduler is written in architecture-independent C and lives in kernel/schedule.c. A few jobs of the scheduler, such as switching processor state or swapping out the address space, are architecture dependent, meaning that the special code has to be written for the specific type of CPU. Consequently, the C method context switch, which switches from one process to another, calls the methods switch2 and switchmm to switch processor state and switch address space respectively. The code for switch2 and switchmm is independently implemented by each architecture that Linux supports. When Linux is ported to a new architecture, the new architecture must provide an implementation for these functions. Architecture-specific files are located in arch/architecture, where architecture is a short name representing each architecture in Linux. As an example, the Intel x86 architecture is given the short name x86. This architecture supports both x86-32 and x86-64. Architecture-specific files for these machines live in arch/x86. The supported architectures in this 2.6 kernel series are Alpha, ARM, AVR32, Blackfin, CRIS, FRV, HA300, IA64, M32R, M64K, M64K no MMU, MIPS, MN10300, PA-RISC, PowerPC, S390, SH, Spark, x86, and Xtensa. A more complete listing of these architectures is in table 19.1 later in this chapter. Okay, history. History of portability in Linux. When Linus first unleashed Linux in the unsuspecting world, it ran only on Intel i386 machines. Although the operating system was rather generalized and well-written, portability was not a concern. In fact, Linus even once suggested Linux would never run on anything but the i386 architecture. In 1993, however, work began on porting Linux to the Digital Alpha architecture. The Digital Alpha was a modern high-performance RISC-based architecture with 64-bit memory addressing. This is a stark contrast to Linus's original 386. Nonetheless, the initial port of Linux to the Alpha took about a year, and the Alpha became the first officially supported architecture after x86. This port was perhaps rather difficult because it had the unwelcome challenge of being the first. Instead of simply grafting support for the Alpha onto the kernel, pieces of the kernel were rewritten as needed with portability in mind. Although this made for more work overall, the result was much cleaner and future porting was made much easier. Although the first releases of Linux supported only the Intel i386 architecture, the 1.2 kernel series added support for Digital Alpha, MIPS, and Spark, although support was somewhat experimental. With the release of the 2.0 kernel, Linux officially added support for the Motorola 68K and PowerPC. Additionally, the architectures previously supported in 1.2 were labeled official and stable. The 2.2 kernel series brought even more architecture support with the addition of ARM, IBM S390, and UltraSpark. A few years later, 2.4 nearly doubled the number of supported architectures to 15, as support was added for the CRIS, IA64, 64-bit MIPS, HP PA-RISC, 64-bit IBM S390, and Hitachi SH. The current kernel, 2.6, brought the number of supported architectures to 21 with the addition of AVR, FRV, Motorola 68K without MMU, M32 XXX, H8300, IBM Power, Xtensa, and a version of the kernel that runs in a virtual machine under Linux known as User Mode Linux. Oh, interesting. Each of these architectures support various chip and machine types. Some supported architectures such as ARM and PowerPC each support many different chips and machine types. Others, such as x86 and Spark, support both 32-bit and 64-bit variants of their processors. Therefore, although Linux runs under 21 broad architectures, it runs on many more machines. Word size and data types. A word is the amount of data that a machine can process at one time. This fits into the document analogy that includes characters, usually 8 bits, and pages, many words, often 4 kilobyte or 8 kilobyte worth, as other measurements of data. A word is an integer number of bytes, for example, 1, 2, 4, or 8. When someone talks about the n bits of a machine, they are generally talking about the machine's word size. For example, when people say that the Intel i7 is a 64-bit chip, they are referring to its word size, which is 64 bits or 8 bytes. The size of a processor's general purpose registers, GPRs, is equal to its word size. The widths of the components in a given architecture, for example, the memory bus, are usually at least as wide as the word size. Typically, at least in the architectures that Linux supports, the virtual memory address space is equal to the word size, although the physical address space is sometimes less. Consequently, the size of a pointer is equal to the word size. That makes sense. Yep. You want to kind of represent an entire memory address with its like native, the CPU's native word size. Additionally, the size of the C type long is equal to the word size, whereas the size of the int type is sometimes less than that of the word size. For example, the alpha has a 64-bit word size. Consequently, registers, pointers, and the long type are 64 bits in length. The int type, however, is 32 bits long. The alpha can access and manipulate 64 bits, one word at a time. Words, double words, and confusion. Some operating systems and processors do not call the standard data size a word. Instead, a word is some fixed size based on history or arbitrary naming decisions. For example, some operating systems might partition data sizes into bytes, which is 8 bits, words 16 bits, double words 32 bits, and quad words 64 bits. That sounds like Windows. Despite the fact that the system in question may be 32 bits. Windows NT-based systems such as Windows 7 employ this naming scheme. In this book and Linux in general, a word is the standard data size of the processor as previously discussed. Each supported architecture under Linux defines bits per long and adds some types H to the length of the C long type, which is the system word size. A full listing of all supported architectures and their word sizes in table 19.1. Okay, so basically today we're using x86-64, so that's going to be 32 and 64 bits. ARM right now nowadays is also 64 bits, although you still have some devices that are still using 32-bit word size. So that's the most important one. Traditionally, Linux implemented 32 and 64-bit variants of a given architecture separately. For example, early in the 2.6 kernel series, there existed both an i386 and x86-64, MIPS and MIPS-64, and PPC-64 architectures. An effort, now complete, has unified these architectures under a single directory in Arch capable of supporting both 32 and 64 bits from a single codebase. The C standard explicitly leaves the size of the standard variable types up to the implementations. The uncertainty in the standard C types across architectures is both a pro and a con. On the plus side, the standard types can take advantage of the word size of various architectures, and the types need not explicitly specify a size. The size of the C long type is guaranteed to be the machine's word size. On the downside, however, code cannot assume that the standard C types have any specific size. Furthermore, there is no guarantee that an int is the same size as a long. Oops. The situation grows even more confusing because there doesn't need to be a relation between the types in user space and kernel space. The SPARC 64 architecture provides a 32-bit user space, therefore pointers and both the int and long types are 32-bit. In kernel space, however, SPARC 64 has a 32-bit int type and 64-bit pointers and long types. This is not the norm, however. Some rules to keep in mind. As dictated by the ANSI C standard, a char is always 1 byte, so across any computer, we always think char is 1 byte. We always treat it that way, so that's good. Although there is no rule that the int type to be 32 bits, it is in Linux on all currently supported architectures. The same goes for the short type, which is 16 bits on all current architectures, although no rule explicitly decrees that. Never assume the size of a pointer or a long, which can be either 32 bits or 64 bits on currently supported machines in Linux. Because the size of a long varies on different architectures, never assume that size of int is equal to size of long, so explicitly calculated. Likewise, do not assume that a pointer and an int are the same size. Okay? Operating systems use a simple mnemonic to describe what sizes their types are. For example, 64-bit Windows is said to be LLP64, means that long and pointer types are 64 bits. 64-bit Linux systems are LP64 long, and pointer types are 64-bit. 32-bit Linux systems are ILP32, meaning int long and pointer types are all 32-bit. The mnemonic is useful for showing at a glance what type of operating system implements its word size, because that choice involves a trade-off. Consider ILP64, LP64, and LLP64. In ILP64, the int, long, and pointer ILP types are all 64 bits in size. Okay, this makes programming easier because the main C types are the same size. Size mismatch between integers and pointers is a frequent source of programming error, but it has the downside that the common integer type is much larger than often needed. In LP64, programmers can use differently sized integer types. So I is 32 most likely, L and P are both 64, but must be mindful that the size of an int type is smaller than that of a pointer. With LLP64, programmers are stuck with both int and long types of the same size and have to worry about the size mismatch between all integers and pointers. Most programmers greatly prefer LP64, the model Linux employs. Opaque types. Opaque data types do not reveal their internal format or structure. They are about as black box as you can get in C. There is not a lot of language support for them. Instead, developers declare a type def, call it an opaque type, and hope no one typecasts it back to the standard C type. All use is generally through a special set of interfaces that the developer creates. An example is the PID-T type, which stores a process identification number. The actual size of this type is not revealed, although anyone can cheat and take a peek and see that it is an int. If no code makes explicit use of this type size, then it can be changed without too much hassle. Indeed, this was once the case. In older Unix systems, PID-T was declared as a short. Another example of an opaque type is the atomic T, as discussed in Chapter 10, Kernel Synchronization Methods. This type holds an integer value that can be manipulated atomically. Although this type is an int, using the opaque type helps ensure that the data is used only in the special atomic operation functions. The opaque type also helps hide the usable size of atomic T, which is not always the full 32 bits because of the architectural limitations on the 32-bit Spark. Other examples of opaque types in the kernel include devt, gidt, and uidt. Keep the following rules in mind when dealing with opaque types. Do not assume the size of the type. It might be 32-bit on some systems and 64-bit on others. Moreover, kernel developers are free to change the size over time. Do not convert the type back to the standard C type, and be size agnostic. Write your code so that the actual storage and format of the type can change. Special types. Some data in the kernel, despite not being represented by an opaque type, requires a specific data type. One example is the flags parameter used in interrupt control, which should always be stored in an unsigned long. When storing and manipulating specific data, always pay careful attention to the data type that represents the type and use it. It is a common mistake to store one of these values in another type, such as an unsigned int. Although this will not result in a problem on 32-bit architectures, 64-bit machines will have trouble. Explicitly sized types. Often, as a programmer, you need explicitly sized data in your code. This is usually to match external requirements, such as those imposed by hardware, networking, or binary files. For example, a sound card might have a 32-bit register, a networking packet might have a 16-bit field, or an executable file might have an 8-bit cookie. In these cases, the data type that represents the data needs to be exactly the right size. The kernel defines these explicitly sized data types in asmtypes.h, which is included by linux/types-h. This is a complete listing. So we have sh, S8, which is assigned byte, U8, unsigned. So these are similar to all the types that you would find in like stdint.h. It'll be like uint32 or something like that. Instead, in kernel, it'll be u32. Okay. So the signed variants are rarely used. These explicit types are merely type defs to standard C types. On a 64-bit machine, they may look like this. Type def signed char is going to be S8. Type def unsigned char is U8. And then when we get down to like long, it'll be S64, U64. And then same thing for, I guess, in 32-bit machine, it's more or less the same thing. Except that it's long for S64 and unsigned long for U64. Okay. These types can be used only inside the kernel in code that is never revealed to user space, say inside a user visible structure in a header file. This is for reasons of namespace. The kernel also defines user visible variants of these types, which are simply the same type prefixed by 2 underscores. For example, the unsigned 32-bit integer type is safe to export to user space is underscore U32 or dunder U32. This type is the same as U32. The only difference is the name. You can use either name inside the kernel, but if the user type is user visible, you must use the underscore prefix version to prevent polluting user space's namespace. Signedness of chars. The C standard says that the char data type can be either signed or unsigned. It is the responsibility of the compiler, the processor, or both to decide what the suitable default for the char type is. On most architectures, char is signed by default and thus has a range from -128 to 127. On a few other architectures, such as ARM, char is unsigned by default and has a range from 0 to 255. For example, on systems where a char is default unsigned, the code ends up storing 255 instead of -1 in or -1 in I. So char I equals -1, that's 255. On other machines where char is default signed, this code correctly stores -1 in I if the programmer's intention is to store -1. The previous code should be signed char I -1. And if the programmer really intends to store 255, the code should read unsigned char 255. If you use char in your code, assume that it can either be a signed char or an unsigned char. If you need it to be explicitly one or the other, declare it as such. Data alignment. Alignment refers to a piece of data's location in memory. A variable is naturally aligned if it exists at a memory address that is a multiple of its size. For example, a 32-bit type is naturally aligned if it is located in memory at an address that is a multiple of 4. That is, its lowest 2 bits are 0. Thus, a data type with 2 bytes must have an address with the n least significant bits set to 0. Okay, the lowest are 0. Okay. So they have data type that is 64 bits. That's 8 bytes. That's 3. So must have an address with that 3 least significant bits set to 0. Okay. Some architectures have stringent requirements on the alignment of data. On some systems, usually RISC-based ones, a load of unaligned data results in a processor trap, a handled error. On other systems, accessing unaligned data works but results in a degradation of performance. When writing portable code, alignment issues must be avoided and all types should naturally be aligned. Avoiding alignment issues. The compiler generally prevents alignment issues by naturally aligning all data types. In fact, alignment issues are normally not a major concern to kernel developers. The GCC developers worry about them, so other programmers need not. Issues arise, however, when the programmer plays too closely with pointers and accesses data outside the environment anticipated by the compiler. Accessing an aligned address with a recast pointer of a larger aligned address causes an alignment issue, whatever that might mean for a particular architecture. That is, this is bad news. So we have an array of characters called wolf. Then we store the pointer of wolf offset by 1 of the address. Okay. Then we say, well, now we're going to cast this to be a pointer to so basically a regular pointer, right? Like a long pointer, depending on whatever architecture, it could be a 32-bit number or 64-bit. Well, actually long, yeah, because long would be 64 and 32-bit. Anyway, so that becomes a 32-bit or 64-bit pointer, and then you dereference, and that could mean bad news. Okay, because then you mess up the alignment. This example treats the pointer to a char as a pointer to an unsigned long, which might result in the 32 or 64-bit unsigned long value being loaded from an address that is not a multiple of 4 or 8 respectively. This sort of convoluted access might look obscure and usually is. Nevertheless, it comes up, so be careful. The real-world examples are generally not so obvious or convoluted. So alignment of non-standard types. As mentioned, the aligned address of a standard data type is a multiple of the size of that data type. Non-standard or complex C types have the following alignment rules. The alignment of an array is the alignment of the basic type or the base type, thus each element is further aligned correctly. The alignment of a union is the alignment of the largest type it wraps, okay, and the alignment of a struct is that in an array of the structure that will have each element of the array properly aligned. Structures also introduce padding, which introduces other issues. Structure padding, so structs. Okay, structs. Structure padding. Structures are padded so that each element of the structure is naturally aligned. This ensures that when the processor accesses a given element in the structure, the element is aligned. For example, consider this structure on a 32-bit machine. Okay, so you have a basic struct here with 1, 2, 3, 4 properties. It looks like you have 1 byte, 4 bytes, and then 2 bytes for short, and then another byte for char. Okay. The structure is not laid out exactly like this in memory because the natural alignment of the structure's members is insufficient. Instead, the compiler creates the structure each such that in memory the struct resembles the following. So it aligns it correctly. So dog is first, add some padding for 3 bytes, so that becomes 4 wasted. 4 bytes with 3 wasted. Long 4 bytes, short 2 bytes, char, fox, and then padding. I think it's trying to get to the last bits being on or off. The padding variables exist to ensure proper natural alignment. The first padding provides a 3-byte waste of space to place cat on the 4-byte boundary. This automatically aligns the remaining types because they are all smaller than cat. Okay. Sure. The second and final padding is to pad the size of the struct. The extra byte ensures the structure is a multiple of 4, and thus each member of the array of this structure is naturally aligned. Note that size of animal struct returns 12 for either of these structures on most 32-bit machines. The C compiler automatically adds this padding to ensure proper alignment. So 4, 4, 4, so 12. You can often rearrange the order of members in a structure to obviate the need for padding. This gives you proper aligned data without the need for padding and therefore a smaller structure. So you can always rearrange the properties so that it's perfectly aligned. So 4, 2, 1, 1. So now you save 4 bytes, you just use 8 bytes for your struct. This structure is only 8 bytes in size. It might not always be possible to rearrange structure definitions, however. For example, if this structure were specified as part of a standard or already used in existing code, its order is set in stone, although such requirements are less common in the kernel, which lacks a formal ABI than user space. Often you might want to use a specific order for other reasons, for example, to best lay out variables to optimize cache behavior. Note that ANSI C specifies that the compiler must never change the order of members in the structure. It is always up to you, the programmer. Okay? The compiler can help you out. However, the W-padded flag instructs GCC to generate a warning whenever padding is added to a structure. That's cool. Kernel developers need to be aware of structure padding when using structures wholesale. That is, when sending them over the network or when saving a structure directly to disk, because the required padding might differ among various architectures. This is one reason C does not have a native structure comparison operator. The padding in a structure might contain gibberish, and it is not possible to do a byte-to-byte comparison of one structure to another. The C designers correctly felt it is best for the programmer to write a comparison function unique to each situation, taking advantage of the structure's layout. Okay. So, byte order. Byte ordering is the order of bytes within a record. Processors can number the bytes in a word such that the least significant bit is either the first leftmost or last rightmost value of the word, so endian. The byte ordering is called big endian if the most significant byte is encoded first, with the remaining bytes decreasing in significance. The byte ordering is called little endian if the least significant byte is encoded first, with the remaining bytes growing in significance. Never assume that any given byte ordering when writing kernel code, okay, unless you are writing code for a specific architecture, of course. So never ever write code that assumes some sort of specific endian. The Linux kernel supports machines of both byte orders, including machines that can select from either ordering upon boot, and generic code must be compatible with either. Figure 19.1 is an example of big endian byte ordering. Figure 19.2 is an example of little endian byte ordering. Okay. So big endian, more significance first, so you read it like left to right. The x86 architecture in both 32 and 64-bit variants is little endian. Most other architectures are big endian. Let's look at what this encoding means in practice. Consider the number 1027 stored as a 4-byte integer in binary. So this, and this. Okay? And then this is little endian. So you read it backwards. So here's the big endian. So you read it in that order. Versus endian, you have to read basically the least significant first and then build it up slowly. So you're building the byte ordering from right to left. So notice how the big endian architecture stores the most significant bytes in its smallest address. This is the exact inverse of little endian. As a final example, here is a simple code snippet to test whether a given architecture is big or little endian. Okay, so given x is 1, so 0, 0, 0, 0, 0, 0, 0 all the way down to 1, you just want to be able to check to see, I guess, if the current address stores a value 1, right? Otherwise, it's big endian. Because the first byte should be 0 if it's big endian, in that case. So this works either in user space or inside the kernel. History of big and little endian. The terms big endian and little endian derive from Jonathan Swift's 1726 satirical novel, Gulliver's Travels. In the novel, the fictional Lilliputians' major political issue is whether eggs should be cracked open on the big end or the little end. Those who favor the big end are big endians, whereas those who favor the small are little endians. The similarity between the Lilliputians and our big endian versus little endian debate is that the argument is rooted deeper in politics than technical merits. Okay. Each supported architecture in Linux defines one of big endian or little endian in as in byte order.h in correspondence to the machine's byte order. This header file also includes a family of macros from include/linux/byteorder, which help with the conversions to and from various orderings. The most commonly needed macros are CPU to BE32, so that's big endian 32, CPU to little endian 32, big endian 32 to CPU, little endian 32 to CPU, I guess byte order. That's what S means, byte order here. These convert from one byte order to another in the case that the byte orders are the same. For example, if converting from native ordering to big endian and the processor is big endian, the macros do nothing. Otherwise, they return the converted value. Okay, so the measurement of time is another kernel concept that can differ between architectures or even kernel revisions. Never assume the frequency of the timer interrupt or the number of jiffies per second. Instead, always use hertz to scale your units of time correctly. This is important because not only can the timer frequency differ among the various architectures, but it can also change on a given architecture from one kernel release to the next. For example, hertz is 100 on the x86 platforms. That is, the timer interrupt occurs 100 times per second, or every 10 milliseconds. Earlier in the 2.6 kernel series, however, hertz was 1000 on the x86. On other architectures, the value differs. Alpha has hertz equals to 1024 and ARM has it equal to 100. Never simply compare jiffies to the number such as 100 and assume that always means the same thing. To scale time appropriately, multiply or divide by hertz. For example, to get 1 second, it's hertz. To get 2, it's 2 times hertz. To get half a second, it's hertz over 2. To get 10 milliseconds, it's hertz over 100. And then, so hertz is just like the X amount of times per second. So then to get 20 milliseconds, it's just 2 times hertz over 100. Hertz is defined in asm_param.h. The subject is discussed further in chapter 10. Okay, page size. When working with pages of memory, never assume the page size. It is a common mistake for x86-32 programmers to assume that the page size is 4 kilobytes. Although this is true on x86-32 machines, or other architectures have different sizes. Some architectures support multiple page sizes. In fact, table 19.4 lists each supports architecture's valid page sizes. So let's see what x86 here is 4 kilobytes. I'm guessing x86-64 also supports 8 kilobytes. So this is just a variety. Okay, so when working with pages of memory, use page size macro as the size of a page in bytes. The value page shift is the number of bits to left shift an address to derive its page number. For example, on x86-32 with 4 kilobyte pages, page size is 4096, so that's 4096 bytes, and page shift is 12, so shift 12 bits. These values are defined in asympage.h. Processor ordering. Recall from Chapter 9, an introduction to kernel synchronization, and Chapter 10, that architectures have varying degrees of processor ordering. Some have strict ordering constraints in which all loads and stores occur in the order prescribed by code. Other chips have weak ordering, and loads and stores are reordered as the processor sees fit. In your code, if you depend on data ordering, ensure that even the weakest ordered processor commits your load and stores in the right order by using the appropriate barriers, such as RMB and WMB. Chapter 10 has more information. SMP, kernel preemption, and high memory. It might seem somewhat incorrect to include symmetrical multiprocessing, kernel preemption, and high memory in the discussion of portability. After all, these are not machine characteristics that affect an operating system, but instead, they are features of the Linux kernel that are indeed somewhat architecture agnostic. They represent, however, important configuration options that you should always assume are available in your code. That is, always program for an SMP preempt high mem system and you will always be safe. In any configuration, in addition to the previous portability rules, you need to follow these as well. First, always assume your code will run on an SMP system and use appropriate locking. Always assume your code will run with kernel preemption enabled and use appropriate locking and kernel preemption statements. And always assume your code will run on a system with high memory not permanently mapped, and use kmap as needed. So in conclusion, writing portable, clean, proper code for the Linux kernel has two major implications. Always code for the greatest common factor, assume anything can happen, and any potential constraint is in place. Always assume that only the lowest common denominator is available. Do not assume any given kernel feature is available and require only the minimum architectural features. Writing portable code requires an awareness of many issues, including word size, data type size, alignment, padding, byte order, sideness, endianness, page size, and processor load store ordering. In the majority of kernel programming, the primary concern is in ensuring that data types are used correctly. Nonetheless, one day an archaic architecture issue will arise, so it is important to understand portability issues and always write clean, portable code inside the kernel. All right, I think this is going to be the last chapter next time we talk.